Hello and welcome to Electrology. In today's video, we'll explore the concept of busbar protection in power systems. We'll cover what busbar protection is, how it works, and go through the different schemes used to protect busbars from electrical faults. By the end of this video, you'll have a detailed understanding of why busbar protection is critical for maintaining the reliability and stability of power systems. So let's get started. Busbar protection is a protective scheme designed to safeguard the busbar from electrical faults. A busbar serves as a central point in a power system where multiple feeders are connected through circuit breakers. Different configurations, such as a double busbar arrangement or a 1.5 breaker scheme, can be used to connect feeders to the busbar. The primary purpose of a busbar is to enhance the reliability of the power system, ensuring power is evacuated and distributed even if a feeder trips due to a fault. To understand this in detail, consider a single bus to which 4 feeders are connected. Here, feeder 1 is the generator feeder, meaning that the power generated is delivered to the remaining feeders, feeder 2, 3, and 4. In case of a fault on any feeder, say feeder 2, the circuit breaker 2 which is associated with that feeder will trip. When this happens, the generator power will continue to be evacuated through the busbar by feeder 3 and 4, thereby maintaining the stability of the generator. However, if all 3 feeders, feeder 2, 3 and 4, trip simultaneously, the generated power cannot be evacuated. Under such a situation, the power station will either operate on house load or trip its generator. From this discussion, it's clear that a busbar configuration significantly contributes to the reliability of the power system by allowing continued power evacuation despite certain feeder faults. Now, let's focus on busbar protection. Suppose a fault occurs directly on the bus, as shown on the screen. To protect the bus from such faults, it is essential to disconnect it from all connected power sources immediately. This requires opening all circuit breakers associated with the bus, circuit breaker 1, 2, 3, and 4. It might seem logical to open only circuit breaker 1, which connects the generator feeder, but this is not sufficient. Feeders 2, 3, and 4 are also connected to the grid, an extensive power source capable of sustaining the fault. Therefore, to effectively isolate the busbar in the event of a bus fault, all circuit breakers associated with the feeders must open. This functional requirement of busbar protection is critical because it ensures the disconnection of all feeders in the case of a busbar fault, preventing further damage and enhancing system reliability. In summary, busbar protection is vital as it promptly isolates the busbar and disconnects all connected feeders during a fault, maintaining the stability and integrity of the power system. The busbar protection scheme employs a busbar differential relay 87, which can be either a high impedance or low impedance differential relay. This differential relay is designed to detect faults occurring on the bus. To understand busbar protection more effectively, let's examine it within the context of a 1.5 breaker scheme. In this configuration, 2 main buses, bus 1 and bus 2, are present. In each diagonal, 2 feeders are connected to these buses through 2 main circuit breakers and 1 tie circuit breaker, as you can see. In this setup, circuit breaker A and B act as the main circuit breakers, while C serves as the tie breaker. Here, feeders 1 and 4 are connected to bus 1 and bus 2, respectively. In this arrangement, separate busbar protection schemes are required for each bus to safeguard both bus 1 and bus 2. The protection implemented for bus 1 is referred to as Zone 1 busbar protection, and the protection for bus 2 is known as Zone 2 busbar protection. Since the protection schemes for Zone 1 and Zone 2 are identical in function and design, we'll focus solely on Zone 1 busbar protection for clarity. Upon closely observing this bus arrangement, you will notice that 2 current transformer cores are installed just after every main circuit breaker. This is for reliability. The secondary windings of these CTs of each vertical are connected in parallel. and then they connect to the relay with a resistance in series in a high impedance differential scheme as shown in the screen. When configuring high impedance busbar protection, special attention must be given to the polarity of the CT connections. Incorrect polarity can cause the relay to operate even under normal conditions, leading to unintended tripping. To better understand the functionality of a busbar differential protection scheme, let's consider two cases to see how the relay responds in each situation. In this scenario, a fault occurs in feeder 1, causing the fault current to be supplied by all connected feeders. The flow of current through each feeder is indicated by a thin dotted blue line on the screen. It's evident that the combined current from feeder 2 and feeder 3 is flowing through the CT1A, but in the opposite direction, moving from terminal 1P2 toward terminal 1P1. By applying Kirchhoff's current law, we can get the sum of the currents from feeders 1, 2, and 3, resulting in a net current of 0. As a result, no current flows through the differential relay, keeping the busbar differential relay in a stable condition, meaning it will not operate or trip under this fault condition in feeder 1. Now, let's consider a fault occurring directly on bus 1. The current flow feeding this bus fault is represented by an orange-colored dotted line on the screen. In this case, currents of varying magnitudes flow through CT1A, CT2A, and CT3A, all in the same direction, from terminal P1 to terminal P2. As a result, the sum of the currents from feeders 1, 2, and 3 will not equal 0. This creates a net current equal to the fault current, represented as fault current equals the sum of currents from feeders 1, 2, and 3. This net current, which is equivalent to the fault current, flows through the differential relay, causing the bus bar differential relay to activate. Upon activation,